Okay, in this video, I'm going to talk about regular versus irregular points. And these are two classifications of singular points, so you should have already watched the video on ordinary versus singular points before you even get started on this one. So assuming we already have a singular point, that singular point is called regular if x minus x naught times p and x minus x naught squared times q are analytic. So essentially you can think about this as meaning that our singular point, our place that the function is discontinuous or not analytic, is in some sense removable by multiplying p by 1 power of x minus x naught and multiplying q by 2 powers of x minus x naught. So let's look at some examples. Okay, so looking at this, my function p is natural log x, my function q is 5. And we mentioned in the last video that natural log x does something weird at 0, so x equals 0 would be an irregular point. Would be a singular point. X equals 0 is a singular point, and if I multiply natural log x times x, so x minus x naught in this case is just x, and x times p of x is going to be x log x. That's still not going to have a power series at x equals 0. So I'm just going to put a sad face. If I look at 5, x squared times 5 is totally okay. That should be analytic. But again, if you fail in either one of these, either one of them is not analytic, then you're going to fail. And so x equals 0 is not regular, so we would say this is irregular. And again, for clarification, all of these points are singular points to begin with. So x equals 0 is an irregular singular point. Okay. As another example, let's look at y double prime plus 3 over xy prime minus 7 over x squared times y equals 0. So again, the only singular point, the place where the denominators are 0, since we have rational functions, would be x equals 0. And so if I look at x minus x naught times p, x minus x naught is just x, so x times p is going to be 3. Does 3 have a power series? Of course it does. 3 plus 0x plus 0x squared plus 0x cubed. Yeah, it definitely is analytic. It has a power series. Let's see, how about the other one? How about x minus x naught, the quantity squared, times q of x. So again, x minus x naught is going to be x minus 0, so just x. So x squared times q of x. And our q of x is negative 7 over x squared. And so the x squareds cancel and give us negative 7. And again, that's a constant function. If we had a polynomial, even better. But it should be analytic. So this one seems to be working out okay. X equals 0 in this case would be a regular singular point. And again, we think about a regular singular point as being a point where the function is not analytic, but it's in some sense a removable problem. By multiplying p by 1 power of x minus x naught, multiplying q by 2 powers, all of a sudden there's no x's in the denominator anymore. We don't have any problems. Okay, so let's look at some more examples. So next example is this guy. And I'm not going to write down all the steps. You could write it out like this and figure it out on your own. But really, I just want to see if I multiply this by, let's see, my only singular point is x equals 0. So I'm multiplying by x. If I multiply this guy by 1 power of x, we're still going to be undefined at x equals 0. So I think because of this guy, we're going to be irregular. This guy, if I multiply by x squared, that's actually going to be a-okay. But again, if you fail either one, you're not going to be a regular singular point. You're going to be irregular. So x equals 0 is an irregular singular point for this particular differential equation. Okay. Again, I see x's in the denominator, which means my singular point is x equals 0. let's see, if I multiply this by 1 power of x, it will be removed. There won't be any x's in the denominator anymore, so yay. If I multiply this by x squared, by 2 powers of x, there will still be x's in the denominator. It will still not be analytic, and so this is a problem. This is going to be irregular as well. And so the quick and dirty way to check if something is regular or irregular is you look at the exponent or the multiplicity in the denominator. If the multiplicity is no more than 1 on the left and no more than 2 on the right, then you're okay, you're regular. If you see a multiplicity of 2 on the left or anything greater than or equal to 2 on the left, you're in problem. If you see a multiplicity of anything bigger than 2 on the right, you're having problems. You're going to be irregular. Okay, so just as an example of what this might look like, let's look at a particular differential equation. Again, all of my A0, A1, and A2 functions are polynomials, but it's not in standard form. To put it in standard form, I'm going to need to divide by x squared, x minus 3 squared. And when I do that, I see at least one thing is going to cancel here, so I can cancel on x minus 3 and simplify that. Let's just rewrite it. So now we only have x plus 3 over x squared, x minus 3, and x plus 1, x squared, x minus 3 squared. Okay, so singular points are places where the denominator is equal to 0, or the denominator being 0, so the function is not analytic. And so we have two singular points, x equals 0 and x equals 3. And so let's look at it. X equals 0, we see a multiplicity of 2 and 2. Our multiplicity should be no more than 1 and no more than 2. So because of this guy on the left, that is going to fail. This is going to be an irregular singular point. X equals 3, we want multiplicity of the corresponding factor, the x minus x naught, to be no more than 1, which is okay. We have an exponent of 1, and no more than 2, which is okay. And so again, if you went through and actually did the x minus x naught times the first, x minus x naught squared times the second, using 3, you would get that the x minus 3 is going to cancel. You're still going to have some x's in the denominator, but you're going to be at least analytic at 3. Yeah, so x equals 3 is a regular singular point. Okay, at this point in the video, I realize that there's a mistake on here. So let's go back and fix that real quick, which is the thing I was just trying to describe. The fact that if you multiply this guy by x minus 3, you're still going to have x plus 3 over x squared, which is not analytic at 0, but it is analytic at 3. So I should have said when I originally defined a regular single point, it should be analytic at x equals x naught. So it doesn't have to be analytic everywhere. It has to be analytic at that particular place. My apologies. I should not have made that mistake.